Hi there. Welcome back to another episode of Rust Remote. This is episode number 6. Today we are going to talk about working with large Rust code bases and takeaways you should take for your own projects, which you might want to start or already are in the midst of, to avoid issues that I've encountered in the past. We're going to start in a few minutes, so it's going to be 3, 4, 5 minutes before I start giving a talk. As always, join us on Discord for discussions. I'll be there available for questions afterwards. And yeah, see you in a bit. So let's start. Well, the slide deck is coming in hot, so if there are any spelling mistakes, please glance across them, ignore them. Let's go. So first of all, a bit of a disclaimer. This is not what my employer thinks. So these are my own opinions, my own experiences condensed into a couple of slides. First of all, the obvious. If you are working on a project, there are a couple of things you should have before you start really working on, really digging into something. And one of that is a goal definition. Like, where do you want to end up in a finite time span, 3, 6, 12 months, and set yourself goals. Like, what do you want to achieve? In which direction do you want to develop a product? What are your priorities? But equally important, like, define non-goals, things you definitely don't want to cover. For library, a non-goal would be, for example, to implement CLI argument parsing. That could be a clear non-goal for that kind of thing. What kind of documentation do you want to provide? Do you want easy entry? Is API level documentation enough for you? But most importantly, right documentation. Also, issue tracking is part of the obvious set of things that you should always take into account, time-wise and effort-wise and mental effort. And also to automate as much as you can of the above. And like, the following slides are going to go into each of those in a different way, a little bit, sometimes in multiple at once. But all of them are necessities for a successful large-scale project, in my opinion. So first of all, in a large project, you're not working alone on that. Usually you have 10, 15, maybe 20 people working on the same code base as you are. So what you really need, as the title says, is guidelines. How do you onboard people? How do you spread information? And these guidelines must be really easy to follow and easy to find. They must be accessible. So naming schemes must be defined explicitly. Like, a lot of introduction material is written by people, and I'm not excluding myself there, working on a project for a long stretch of time. And at some point, certain phrases contain more information than you'd think at the first glance. Like, there is context attached to certain phrases, and this needs to be explicitly specified or stated somewhere in a document. And the easiest way to do that, in my opinion, is to provide links in pull requests. Like, when you open a pull request, no matter if it's GitLab, GitHub, or whatever your preferred service is, if it's Bitbucket, then I'm sorry for you. But all of these provide measures to, like, allow you to template your pull requests, like what the person creating a pull request sees, and there it's easy to embed links. So it's accessible, it's easy to find, and if you write them correctly, they're easy to follow as well. And all of these, like, that's the first step to get people motivated to work on, like, to reduce the strain. And as part of those templates, it's also good to include, like, what are the expectations that you as a reviewer have on the content of a pull request. Like, try to be explicit. Like, trying to be explicit keeps people motivated to work on something because they know exactly what the expectations are. So this is a little bit like setting the expectations or goals of a pull request. On a more practical front, like, tooling is ubiquitous. So it's everywhere. It's everything you do with Rust. It starts with cargo for small projects and ends with SC cache for larger scale projects. If you're an embedded guy, then hardware means you have your debugger, you have your probably some kind of embedded device that you want to work on. And these are things which should just work. Like, you should not have to deal with that on a daily basis. So this is more a get your setup straight. Like, figure out a setup for yourself that gets out of your way and lets you work. Focus on something that you really care about. Now, this sounds really, really obvious, but with a fast-moving tooling environment like there is with Rust, this is not so easy. Especially when the projects become larger, then you're all of a sudden facing limitations of cargo. How do you, for example, release a project with 50 subcrates, all with different versioning? So if you kind of dig one step deeper into it, now we are finally at the source code level, which is probably what you all expected. Like, the first thing, and we already had a couple of iterations in the Rust language ecosystem, in the Rust library ecosystem. It started a long time ago with error chain, and then iterated quite a bit, and now we are at this error or anyhow or ire. And there's a very important distinction that there are types which are better suited for libraries, and there are error libraries which are better suited for applications. But at the very beginning of a project, it's sometimes not so clear, am I just creating a binary, or am I just creating, or am I creating a library and just like my binary is just a small wrapper? And if you think about it, then it's a lot easier to go from this error to anyhow than it's the other way around. So it's always a good idea to define, if you have large modules, then it's better to define error types per module and then have kind of a stack of errors. So you have an enum, and one enum variant is a type of another, is an error type of another module, and have that down to the point where you only have the main function, and there you can then use anyhow or ire and use all the fancy backtracing features and get all the advantages of both ends. And in the end, if you decide, oh, this part of my application actually is something that I could ship as a library, it's a lot easier to extract that than backtracking from a almost untyped error with anyhow or with ire, which sometimes even likes basic trait implementations. It's just way harder to reverse that, because then all of a sudden you have a huge pile of changes ahead of you, and it's only like chores. It's only introducing a new error enum here, it's a new error enum there. So if you start from the very get-go with a defined error type per module or per subset of modules, then you're much better off in the long run. Again, large-scale project. Another thing is to avoid glob imports. So in a small project or very small crate, you can just a couple of modules, use super : asterisk, and you're good to go. But if your project scales up, the chances are good that you might encounter situations, and actually quite a bit of those, where you have overlapping struct, enum, or type variant, type names. So all of a sudden, if you use wildcard imports, you will face error messages which tell you, yeah, this is exactly the type name that you wanted, but it doesn't work because it doesn't implement this or that trait. And that can be kind of confusing if you're facing a couple of tens of thousands of lines of code. So avoiding blob imports is a good best practice, which I'm not a big fan of this. I'm a glob import. I am guilty of breaking this rule, but as soon as you scale it up, it just doesn't work anymore. So Rust has a couple of advantages, but also a couple of disadvantages. And one of the disadvantages is that compilation takes quite a bit of time, especially if you have generic heavy code. And so you don't want to necessarily recompile that every time when you just change a line of code. And one approach to that is to split like large projects into many, many small crates. And then most of the crates don't have to be recompiled. And that saves you a lot of time. Another way of speeding things up is just avoiding linkage entirely. So with the first one, you avoid recompilation of a big chunk of code, big parts of your code base, but that's bringing you back to linkage, because now all of a sudden you have a lot of things to link. So linkage time is going to explode. So for your day-to-day development, most of the time it's sufficient to just run cargo check, and that avoids linkage. If you have to link because you want to, if you want to run unit tests or documentation tests, which both include linking, then it might make sense to switch your linker, especially on Mac OS X. There are really fast linkers compared to the default ones. Like really fast is always relative, and spend some time digging into that. Avoiding linking is precisely cargo build being converted to cargo check for your daily workflow. If you, or at the implementing stage, and not so much at the debugging stage, then it's usually sufficient to run cargo check. Test modules are commonly guarded by config test. And generally that's good enough. I just recently read a blog post that moving them to separate files actually gives you a speed up. So that's something that you should keep in mind, especially if you have many tests. As your code base grows, you will see that some things are very repetitive. Like you implement the same trait for a lot of different types. Sometimes you need helper traits for integer types, which are not part of the STD. And these types are, these traits are really boring. Mostly they are just marker traits, and they are just really repetitive. So that's the point where macros come in. And for another example, when you write test cases or integration tests, then all of the test setup and the test teardown are also very mundane tasks. So it's very repetitive code without much knowledge gain, and you don't need a big brain for those to do what you expect. And the issue with that is those macros are usually very, very underdocumented. So you have this macro, which is arguably a little bit harder to read than regular Rust code. And yeah, but at the same time, it generates a lot of code, which is kind of hard to debug. So it's very, very important to document extensively what the expectations for the inputs are and what the expectations for the outputs are. Now, the issue with that is that usually these macros are just internal, like just implement the trade for primitive types or just do some test setup thing. And that's about it, what they do. So they never see the day of light. They are never part of the generated documentation. So yeah, usually nobody cares about if they're documented or not. But that's a big problem because reading of them takes arguably more time. So documentation there is kind of extra important to save other people's time. And the same thing counts for Proc Macros as well. So Proc Macros are using an API to the compiler to modify the abstract syntax tree. Very rough description. And there you have to specify the errors manually. So there is a function, and that's called compile error, and that displays a compile error. And you have to pass a span, and that span is then highlighted with the little hat symbols where you actually made a mistake. Now, usually you generate a lot of code, so it's not that easy to exactly specify where the source of that error is, but it's therefore even more important to exactly state what the expectation was, where it was violated, and exactly like best effort, where did it go wrong? Where was something else expected? And what was the guess before that? Because usually for the proc macro, you have a couple of variations of input, like you want some things to be optional. For example, for Saturday, you want annotations of an enum variant to be initialized with a certain default inner value, and that value has to come from somewhere. And that function will provide that inner value, so you have to specify it, and that's usually done with a proc macro. You annotate that at the enum and at the enum variant. Just example. And there you have to think about the ergonomics for the user. The user doesn't know what you wrote in your proc macro. He's probably never going to see the proc macro code. And even if he does, that's Rust abstraction, macro rules, and kind of sidestepping to that is like direct modification of the syntax tree. So you're at a different meta level, I'd say. And that needs even more practice. Like macro rules is a kind of half god, and proc macro is god in the Rust world, just to put it into perspective. So with great power comes great responsibility, and with that said, like you really should put a lot of time into crafting proper error messages when you write proc macros. Otherwise, you will be unhappy because of the amount of bug reports, and your users will be unhappy because most of your users will just think, well, this is a crap library, it's broken, when you really just like screwed up your error message. There's a question. Do you have a use for custom integer types that isn't fulfilled by the Rust num ecosystem, num begin, num traits? I'd say it depends. Sometimes you don't want to drag in the num ecosystem. Sometimes you want to be as lean as possible. And there are cases, like generally you're correct, num is really extensive. But there are cases where I simply only want a subset of integer types to have certain traits. So I want only U16 to U64 have a certain trait implementation and not all of them. And that's where I think num is not the right choice. So when you look back like 2-3 years, I think it was 3 or 4 years when Tokyo became kind of big, like Futures 0.1. And the associated, not sure to call it hype or not, but the futures really like got traction in the Rust ecosystem. So at that point, a lot of people like ask themselves, should we jump on the futures train or on the async train? And to some extent, a lot of things have changed and some didn't. Like right now, there are still issues with async. Like they're a lot smaller than 4 years ago. So with the async keyword, the ergonomics are a lot better. There's still a couple of corner cases which can bite you once in a while. For example, it's a really hard problem to get async traits. So you can async traits without boxing. Right now, there's a bit of a stopgap, which uses like boxed in future trait as return types for async trait annotated trait types or traits. And yeah, so I'd say it depends. For a lot of use cases, it's probably a good idea to use async, but there are also use cases where it's not necessarily a good idea. So if you have a lot of blocking tasks, for example, you're spawning a lot of tasks in the sense of system processes, then it might be better to use a actor pattern compared to async, or maybe a mix of both. So that's really, really very topic specific. A colleague of mine wrote a blog post a couple of, I think, days, might have been a week already, where he wraps up his experience and the pitfalls of the current state of asynchronous Rust. And I really recommend reading that. This is a link, so if you download a slide deck later on, yeah. There's another topic, and that was also partially covered by the previously mentioned blog post. That blog post kind of touches on how do I abstract across things. So in this case, I have 2 examples. One using, like the first one uses dynamic dispatch, and the second one uses a generic. Yeah, so if your background is more from a Java world or object-oriented world, then the first one might be more appealing to you. If you're more from a C++ template Ninja kind of background, then the second one might be more appealing to you. And there's a bit of a rule of thumb when to use one or the other. The first one shifts a certain amount of computation from compile time to runtime, and has the advantage that it's extendable by other libraries, like easily extendable. And the second one is a little bit heavier on the compile time, but you don't have the dynamic dispatch at runtime. So to some extent, it's a matter of taste. If you have a really complex system, like really, really complex, hard to oversee, many small components, many moving parts, and you want your user to easily extend your kind of inject their own types, then the first one is sometimes easier to handle. Simply because you don't have to use generics everywhere. Because all of a sudden, if you want to make use a specific feature of an implementation of the trait, which is stupidly called trait in here, then you have to kind of make everything in the path a generic. There's no way around that. Whereas in the first one, it's easier to just use a type alias and just use it like a regular type, and you're done with it. So it's more about developer ergonomics than anything else. Also note that the first one will issue a warning if you use it like that. So again, that's a number depends on the use case. For smaller crates, smaller libraries, it's probably good enough. If you thread through generics, because the path from where you need that information of your type and where you have it is usually not that far. So it's a couple of tens of functions, worst case. But as soon as you have big interconnected systems, then the first one might be more sensible. So with the above said, that kind of plays into my next point. It's about the architecture, like how you implement things. And the bigger your system becomes, the harder it becomes to detangle it and write mocks for certain subsystems. So if you have tightly interconnected parts of your system, then you want to inject certain behaviors for your integration tests. So you can test a different subsystem and know what the other subsystem kind of does. So you have input stimulus and you have a mock subsystem or a subsystem that is mocked and generates certain errors. For example, a mock subsystem that always pretends that I/O went wrong and gives you an I/O, or a file doesn't exist, file is not accessible. Something that you usually don't cover in your integration tests. And with that, you can test your subsystem on the test for behavior against those errors. And that's something you have to bake rather early-ish into your system architecture or design, because otherwise you'll suffer quite a bit of pain. It's like reintroducing a basement after you built the house. That's kind of the level of pain you're going to face. It's possible, it's been done, but it's just not fun. So start with the basement and then build a house. I started working on a Zcash, which is potentially going to be forked into Cashbot. And I found the patterns there rather interesting at the beginning, but right now I start to understand. So, for example, they introduced a trait which they use for spawning processes. And with that crate, with that one single crate, and passing around a executor pattern, passing around the executor, which is a boxed in of that command creator, with that alone, they have the possibility of simulating arbitrary process failures. And that allows them to test for a lot of things that you will encounter eventually in production, but you're not encountering in your unit tests. So it's a really small piece in the code base, but it threads through everything that's using process I/O. There's a question. Do you have any suggestion learnings regarding to hexagonal or clean architecture? I'm not sure what to respond to that. Like, I've read a little bit about hexagonal architecture and design patterns, and like, to me, this is all very, very impractical. To me, it's trying to abstract away from a programming language that has certain strengths and certain weaknesses, and tries to make it something generic, something like abstract that you can then simply process in an abstract manner. That works to some degree, but it works better for some languages than for others. So if you have a language which has like one particular like one base principle, like with Java you have OOP, and there I think you can apply that really well, or any kind of design or architecture concept. But if you use a language which has more than one principle built into it, then I find these things rather unintuitive to use in practice. So what I prefer is try, fail, try again, fail better. So what I do is based on experience. I hope that answers the question. Another thing that you would want to avoid is using stringly typed types. And in the end, like, this is just the quick shortcut. You want to get something working. So I want something that's serializable, that's fast, that's easy to manipulate. So I just use a string and I'm done. For example, CLI argument. And so a CLI argument in itself is just a string, and that's fair game. But as soon as you start to give that string meaning, so you only have a triplet of enum variants, which are the only correct values that it can come out of your argument parser, then a string gives you an infinite, almost infinite amount of variations, but you only need 3. So 3. So in that case, you should shrink your the space of variation, like reduce your variation whenever you can. If you only need 3 variants, use a type that represents that exactly. So in that case, take the pane and use a wrapper type, use a type alias if you're lazy. Eventually, as your system grows, you'll be really happy if not every argument is a string. In like the same thing is if you use numbers, for example, like timeout in futures is a common theme. They use a timeout is one value. You create another timeout, there's another value. You create a third timeout, it's another value. And essentially you run into really awkward bugs because timeouts are probably not your common theme, where you have not races in the traditional sense, but unexpected behavior just based on inconsistent timeout behavior. So creating an additional constant variable that just says, this is the timeout for all requests of this type, and then use that consistently throughout your file or your code base or your module or your crate. That helps a lot, both readability, adjustability, and maintainability in the long run. I have no idea why this slide is blank. So there's supposed to be a title called matrix. This slide is a little bit more for those like doing embedded systems with connectivity or backend systems. For CLI systems, this is not really that big of a deal. So there are various ways how to debug your things. You can use your debugger, you can use printf, you can use matrix. So matrix are a couple of different things. So you have matrix collectors, and Jaeger is a particular matrix collector. So you annotate your things with span. So it's a little bit like Tokyo tracing, but it's more made for multi-process, horizontally scalable backend services, where you can relate identifiers across nodes with each other. So you get a kind of a good big picture. And you get a Gantt chart, what happens when, what did take, how long, which span was related to which span, and things like that. So that's a really nice tool. It's a little bit hard to use at the beginning, and things are not that trivial to read. That's a really nice tool. Another thing is you could, on the collecting side, you can use something like InfluxDB. This is not exclusive. You can use OR and both of them. With capacitor, like these are the things that I personally like because they just tend to work. If you like Prometheus and Grafana, same thing. It's not a replacement for Jaeger. I don't know of a replacement for Jaeger. But these are maybe open telemetry, but that's slightly different. And with these things, you kind of get like the bird's eye view of what your whole system does. So if you have a fleet of embedded systems or edge nodes, then with that you get a concise picture of if you have, for example, a time-based issue. So, for example, on embedded, if your RTC register is overflowing and you're not handling that properly, you get an interrupt which you did not expect, and there's no interrupt handler registered, and you go into the hard fault handler, and boom, you have like with a standard deviation of a couple of seconds, a couple of tens of thousands devices reset. And that's something, this is kind of the tooling that you would use to see that. Or you have performance issues for like large-scale backend services, and you don't really understand like why is it taking long, or under which circumstances, and then a combination of Jaeger and InfluxDB could help pinpoint that. But this is already at the point where things are already deployed. So things are out there. You shipped them. You thought they were good. But usually it's better to catch things earlier. So this is the matrix at CI slide. So actually, no, this is the matrix performance slide. And so I'll get back to the previous point about catching things early. Like this is about performance. Other types of projects require you to have like very small scale, fine-grained performance measurements. So one thing to do there is perf and plot the perf data in some sane way. And one way to do that is using flame graphs. Another way to measure, like statistically measure performance of certain benchmarks that you wrote manually for one particular crate. So this is at a scope of like one crate, one benchmark, where this is best suited. So in a small scale, you want performance on that scale, which is by definition rather small. So this all kind of gives you hints on what micro optimizations you want to do. So after you see your big system and it's all slow and you don't like it and you don't want it to be faster, then eventually you'll figure out which part of the system is slow, and then you take that subsystem, you take it apart, and you figure out what particular like crate is wrong or slow, and then you start benchmarking that with criterion. And if you want to have cache misses, then you have from the criterion alpha the IAI crate, which uses wall grind to get cache hits and cache misses. So these are nice tools to do low-level optimization. Yeah, avoiding manual labor. So on the implementation scale, that's solved by macro rules and proc macro. You've seen that before. Trait abstractions also help. But you also have that on a very pragmatic scale. Like how do you verify code that moves into your code base is correct? Small system, again, you maybe have one or two features, which is fine. Bigger scale, you all of a sudden, you tend to have more feature flags. And that means your test coverage is harder to get. Sometimes you need special hardware to test certain things. For example, one of my pet projects is still the Juice machine learning framework. And for some of the tests, you need an NVIDIA GPU. Like, I didn't own an NVIDIA GPU for a long time. And it's not really pricey to rent a AWS server for NVIDIA GPU for a full month. And so what you want to do is you want to be able to either spawn those instances on demand, or you buy one, which is what I did, and then set up your CI on a spare PC or a spare PC parts that you have, and have a custom worker. And this is like one kind of viewport on how to solve part of it. So automate what you can. So you integrate whatever dependencies, physical or non-physical you have, and put it into your CI system. But before you can do that, you should also use the cargo power. So earlier we were talking about, yeah, one big crate is bad because it's bad for compilation time, but it's kind of easy to manage. Because when you have many, you get a couple of issues with releasing heterogeneous versions of many crates. And yeah, so Cargo has a lot of plugins. One of those is Cargo Unleash. A couple of features from the default Cargo, like the inbuilt features, are also useful, like the workspace feature of Cargo, where you can collect a lot of small crates. So if you solve that, so let's assume you solved all the small crates issues, you can release them conveniently, you can build them conveniently, everything is nice and candy. Just the amount of effort that you need to integrate everything into your CI is non-trivial. All of a sudden you have a lot of dependencies. You might not even know that some of your dependency crates require certain Rust C versions. Some of them require certain features of nightly versions. Some of them only built with nightly versions. Some of them include C libraries. OpenSSL is one of the most known offenders there, causing, yeah, I think I lost years of my life just integrating OpenSSL. And yeah, different story. So if you have all of those dependencies, your CI system needs to be able to satisfy those in a reliable, reproducible way. And you also need to be able to debug what's happening within your CI. And that's a huge amount of effort. Again, example choose. Just keeping things afloat, like keeping the CI green, based on a C library that's changing its ABI in small version increments is, yeah, it just consumes a lot of time. And that's something that you should not underestimate. If you have a small cargo, again, example, small one, things you don't need to worry about is what kind of CI system allows me to access hardware features? What kind of CI system allows me to spawn a KVM instance on the same machine I'm running on? What kind of CI worker allows me to access my NVIDIA GPU? And to combine that with reproducibility and security, because pull requests are like assuming you're on GitHub and or GitLab and you have a pull request and your CI just arbitrarily executes code, then that's a security concern as well. So all of a sudden you're in the midst of figuring out containerization, seccomp rules, and SLInux to make sure nothing is escaping your local worker. And one example for that is, for example, GitHub Actions, which makes almost zero guarantees of whatever is executed on their custom worker. And so if you're conscious about security things, that's a big deal. That's a no-go. That's something that kind of rules out GitHub Actions right away. And yeah. So again, personal opinion. I've been using Concur CI with varying amounts of grievance. And so far, it's ticking the most boxes I've seen so far. It's not going for the custom case, but it allows you to do what you need to do. Yeah, I'm going to leave it with that. You can Google it yourself. So this list is really not complete. Like, this is just a glimpse of what, now almost 4 years of Rust development, and like a couple, yeah, like I transitioned from hobby projects slowly into full-time, and like this is just a glimpse of like the first things that you will experience once you work on larger code bases. There are still a lot of things not covered, like Linkage, for example, is a way to speed up compilation for Rust crates by using cloud-based buckets for artifact storage, and yeah, that speeds up quite a few crates quite a bit, but only if you have many small crates, not if you have one giant big crate. And linkage is still a bit of an issue. Like, that's probably the part where I spend most of my waiting time every day. And that's about it. If you have any questions, I'm happy to talk about this more. I'll be in Discord. Thanks for joining, and hope to see you next time.